Dear students, today we'll be starting with the chapter that is process concept. The topics which we'll be covering in this chapter includes the concept of the process, process states, process scheduling, various operations in the process, and at last the inter-process communication. So let's begin with the concept of the process. So if we talk of early computer systems, only one program was allowed to execute at one time. That program used to have the complete control of that system and was able to access all the system resources which were required to execute that program. On the contrary, the contemporary computer systems allow multiple programs to be loaded onto the memory, and all these programs can be executed concurrently. As far as a process is concerned, it is a program in execution. So, a system may consist of a collection of processes, and these processes may execute some user code or they may execute some operating system code. The processes which are executing may execute concurrently or they may execute one after the other. It all depends upon the potential of the machine on which the processes are executing. If we have a uniprocessor machine, in that case only one process can execute on that machine at one time. On the other hand, if we are having a multi-processor machine or a machine with processor having multiple number of CPU cores, in that case, multiple processes can execute concurrently. An operating system executes a variety of programs. A batch system executes jobs, whereas a time shared system executes user programs or tasks. If a user can execute only one program at a time, still at the back end, the operating system might be running various internal activities to keep the system in working state. All these activities can be called as a process or processes. So, a process can be thought of as a program in execution, and this program needs resources to execute. The resources required may be it may include CPU, memory, or various input output devices. The resources might be allocated to this process when the process was created or when it is executing. When the process is executing, the status of current activity of that process is represented by the value of the program counter and the processor registers. The execution of the uh, process progresses in sequential fashion. That is, instructions are executing one after the other, so the program counter holds the address of the next instruction which will be executing after the current instruction has executed. The number of registers are also associated with the processes. They hold the intermediate values which keeps on changing when the process is executing. So I am talking of this program counter. You must have read this term in your computer architecture also. So as far as this program counter is concerned, it holds the address of the next instruction which will be executing after the current instruction. For example, suppose we are having a set of instruction, so they are executing one after the other. So suppose that as of now, this is the instruction which is executing. So after this, if there is no jump statement, then obviously, or branch statement, then thereafter this is the instruction which will be executing. So basically the program contains the address of this instruction. The moment this instruction is executing, thereafter the program counter will hold the address of this instruction, and so on. It so as we are saying that the program is the process is executing in a sequential fashion. So the program counter contains the address of the next instruction which will be executing after the current instruction. So now let's see how a process looks when it is stored in the main memory. Or when basically, if we talk of the memory allocated to a process, this memory allocation is divided into multiple parts. This includes the text section, which has the program code or the executable code. It also contains data section, which holds the global variables. Then it has a heap section. Basically, it is that memory which is dynamically allocated during the runtime. It also has a stack section which contains temporary storage for function parameters, return addresses, and local variables, which comes into picture when the functions are invoked. So as far as the first two sections are concerned, that is the text section and data section are concerned, the size of text and data section, they are fixed. That is, they do not change during the program's runtime. However, the stack and the heap section, they can shrink or they can grow dynamically when the program execution takes place. For example, every time when a function is called, an activation record of that function containing function parameters, local variables, and return addresses is pushed onto the stack. The activation record is pushed onto the stack, and when the control is returned from the function, the activation record is popped from the stack. Similarly, the heap will grow as and when the memory is dynamically allocated, and it shrinks when the memory is returned to the system. So if you see this slide, basically it depicts how a program is represented in a memory. We have taken an example of a program written in C language. So in this program, if we see, it contains a header file followed by a declaration of two global variables, that is x and y, where x is as of now uninitialized and y is initialized. Then it contains a main function, and this main function contains two arguments. One is integer, and the second one is a character pointer array. Apart from this, the main function also contains two local variables, that is integer variable I and a pointer variable values. Uh, in addition to this, we are also using a malloc function to allocate the memory. So if on the left side of the screen you can observe a memory basically is divided into four sections, that is text, data, heap, and stack. So as far as text and data part are concerned, we have shown it as a fixed one, that is there is no change in these sections, that is neither did they grow nor they expand, they are having a fixed size. But as far as heap and stack is concerned, you can see over here we have shown an arrow which depicts that they can be shrinking or they can be growing depending upon at what stage the program is going through. So the stack section basically contains the activation record of the main function, because as of now the main function is executing. So the activation record for main function, which includes the function parameters, that is argc and argv, they are placed onto the stack. It also contains the local variables. So the local variables of the main function, in this case one is pointer variable and second one is integer variable, they are also the part of the stack. Apart from this, it also contains the return address of the of this main function. This return address basically points to the address of that instruction which will be executing when the control is returned from the main function to the calling function. Once the control is returned back from main function to calling function, the activation record of the main function is popped from the memory. Further, in the main function, we are using a malloc function, which is an inbuilt C function, which is used for allocating a block of memory. This is stored in the heap section of the memory. Basically, this is stored in the heap section of the memory. So if I would like to explain you it in a bit of a better way, let's assume that as of now function f1 was executing, and f1 contains some set of instructions. Let's say we number them as 1, 2, 3 and 4. So as I've told you, the process execution takes place in a sequential fashion. So as of now, instruction 1 was executing and program counter was holding the address of instruction number 2. So when instruction number 2 was executing, program counter was holding the address of instruction number 3. Let's suppose that this instruction number 3 is basically calling another function, and let's say f2 over here. So that means after this 3, it is not the instruction number 4 which will be executing, but the control has to shift from the function f1 onto function f2, and let's suppose that function f2 is this one. So we shift from this place of execution to a new function. So when we are switching from function f1 to function f2, so what happens over here is, first of all, the activation record of this function is basically placed onto the stack. So what all things are the part of this activation record? That is the function parameters, that is the local variables, and even the return address. They all are getting memory in the stack part. Fine. At the end, when this entire f2 function has completed its execution, the control is returned back to the place from where we came over here. So we came over here from instruction number 3. That means once the execution of f2 is over, we switch back to the place from where we came. So we came from this place. That means once we come over here, then thereafter this instruction number 4, which was otherwise to be executed earlier, will execute now. So in this case, f1 is again active. That means the activation record of f1 is activated in the memory. It is available in the memory. This is how the activation record plays a role with regard to the execution of the current function's execution. I hope you got this point. So a program is a passive entity, like a file holding a list of instructions that are stored on a disk. Fine. On the other hand, a process is an active entity which has a program counter that specifies the next instruction which will be executing after the currently active instruction. For its execution, the process has a set of associated resources. A program becomes a process when an executable file is loaded from the disk onto the main memory. And this can be done just by clicking the icon of the exe file, or by giving a command which will execute the exe file. Further, two processes that are associated with the same program, I repeat, two processes that are associated with the same program are considered two separate execution sequences. For example, let's take the case that one user has invoked multiple copies of web browser. Each of these copies is considered a separate process, although they may have same text section, but other sections, that is data, heap and stack, they may vary. For example, let's suppose I'm working with the Google Chrome, and or a user is working with the Google Chrome browser, and that user has basically invoked multiple instances of the browser, instance 1, instance 2, and instance 3. That means three instances of browser are right now working. On the first instance, suppose the user is using google.com and is searching something. On second instance, suppose the user has opened YouTube, where he is watching some video. Fine. And in the third instance, suppose the user has opened Gmail, and maybe he is reading some mail over there. So if you see over here, there are basically, though there is only one browser which is opened, and we have opened its, or the user has opened its three instances, that is multiple copies of that web browser are opened. Each of these instance or copy is considered as a separate sequence or a separate process. And though these instances may have same text section basically, but the other sections, that is data, heap, as well as stack, that may vary. I hope you got this point. So this is all with regard to this lecture. So in the next video we'll be covering about process state transition diagram. Thank you.